Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good day. My name is Aiman Iqbal bin Ibrahim and my matrix number is 208198.
Hi, my name is Ni Akif Haziki bin Rahidi. My matrix number is 208150.
So today, me and my partner, Nick Akif, will present to all of you on how to design a MOD-6 synchronous counter by using the flip-flop. So how do we create this MOD-6 counter? First thing first, we need to make a state diagram. So what is a state diagram? Given the question is an MOD-6, which means that we need to arrange 6 digits of binary number in ascending order from 0 to 5. Some of you might be question, why not we arrange the number from 0 to 6 because it is an MOD-6. Now here's the trick one. 6 MOD-6 means that there are 6 digit, 6 binary number, and we need to start from 0. So the 0 is counted as the first number and 5 is counted as the last number, the 6th number. So 0 in the binary is 000. 1 in binary is counted as 001. 2 in binary number is 010. 3 in binary number is 011. 4 in binary number is 100, and 5 is the 6th number is in binary number is 101. So as the number is arranged in ascending order, in the specific order, the rotation of number should be turned back from the last number to the first number. So it will be a complete rotation from the first, second, third, fourth, fifth, and the sixth, and then it will return back to the first number. So it will be a complete rotation of a state diagram. So, second step on making an MOD-6 synchronous counter by using the flip-flop is to make a state table. So, in this state table, there are 3 different types of table. The first one is the present state table. Each table in this state table are categorized in each column as Q2, Q1, and Q0. So, let's go back to the present state table. In this present state table, we need to arrange the binary number by following the state diagram from 000 to 101. Next, the second one is the next state table. In the next state table, we need to arrange the number one state above the present state, which means that the first number in the next state table is 001, because in the present state the number is 000, which means the last number in the next state is 000, because the last number in the present state is 101. So you can see here the number complete the rotation, the present state and the next state. So how about the last table? The last table is known as the input table or the D input table because we are using the D flip-flop. So as the present state and the next state using Q2, Q1 and Q0, but in this input table, the D table, we use D2, D1 and D0. So this is the important one of the most important steps that we need to understand. So the input table should be the same as the next state table. So the D2 column shall copy from the Q2 from the next state, and the D1 need to copy from the Q1 from the next state table, and the column D0 need to copy from the Q0 state table. Is it right? So if we make a D flip-flop, just copy from the next state. Why do we make a next state table? Because in this state table, basically when we find the next state, we want to find the input table. So if we want to search for the input table, we need to make the next step table first in order to find the input for the flip-flop circuit that we are going to do after this. Before that, we need to make a K map and then the circuit.
To implement the kind of map, we will need to use the truth table that we get in ELA. From the truth table, we know that we have three different variables, which are Q2, Q1, and Q0. So our K maps will be whether 2 rows 4 columns or 2 columns and 4 rows. So for this video, we will use 2 rows and 4 columns. So we move to D2 K maps. For the D2 K maps, first we will need to look at the truth table and search for the height input. So from the truth table, we know that the height input will be 0, 1, 1 and 1, 0, 0. So in the kind of maps, we will write once at both input that have 0, 1, 1 and 1, 0, 0. So next is, since our truth table only have from 0 to 5 input, so 6 and 7 which are 110 and 111 will be the don't K. So in the K maps, we will put don't K at 110 and 111. So and for the rest, we will just put it as 0. So now we already pull the kind of map. So we just have to search the function of D2. So the function of D2 will be Q1 Q0 plus Q2 and Q0 bar. So the D2, now we have the D2 functions. So we move on to D1 and D0. For the D1 and D0, we just have to make it as like the yearly. So we doing the same thing, search for the high input, and we put the donkey, and lastly we just have to find the function itself. So for the D1, we will get Q2 bar, Q1 bar and Q0 plus Q1 Q0 bar. So for next is for the Q0, we will get only Q0 bar. So now we have found all the functions of D. So we can straight to the logic diagram. For the logic diagram, as right now we already have all the things that we need to construct and draw the logic diagram. So the logic diagram will be as be shown.
So to make a circuit in the multi-sim, we need just to follow the circuit that are from the logic diagram that drew before. So in the multi-sim software, the one thing, or I may say two, but the most importantly, the one thing that most important in this multi-sim software that are not present in the logic diagram is the 4 channel oscilloscope. So the 4 channel oscilloscope function to see or to observe the waveform of the output from each input in the flip-flop. So, and then one thing that we add here is the probe, which means that as you can see here, PD2, PD1 and PD0. So the PD2 represent the output from the D2 input, while the PD1 probe represent the output from the D1 input, while the PD0 represent the output from the D0 input. So if the waveform turns 1 in any output, the probe will be lights on.
As you can see here, for the waveform, the yellow line will be the clock, while the blue line will be the Q2, and for the orange line will be the Q1 output, and the last one, the green line, will be the Q0 output. So take note that when the wave height, it will be the same as 1, while when the wave is low, it will be same as 0. So to know that our waveform is true and right, we just need to compare it with our truth table in yearly. So let's we check it. So for the Q2, we have the input in the truth table as 0000011. So as you can see in the waveform picture, it seems that our Q2 is correct. So that's we check it for the Q1. Q1 will be 001100. As you can see here also, as you can see, it's also correct. So for the last one is Q0. Q0 will be 010101. As you can see here, the Q0 also correct. So it seems that our waveform is correct and right. So this is how the waveform work. It will be just form just like the output that we design as we created. To summarize our video today, as a conclusion, we can design, construct, and test the MOD-6 synchronous counter in multi-sim software. As we go through this lab, we can observe that the synchronous counter are easier to design than a synchronous counter, since the clock input across all the flip-flops use the same sources and creates the same clock signal at the same time. As it have a common clock pulse, all the output change simultaneously, and there is no interpropagation delay. I think that's all for this video. I hope you enjoy and like our video, and thank you very much.